Hi everyone. We have a new session for the DKRZ series, and this time we are going to speak about machine learning. And I am so happy that we have two experts for today. That they are Christopher Cado and Tobias Weigel, and they will speak about the services we are providing in DKRZ in relation to machine learning. This is, as I said, a series, so there will be more talks. Next week, we have another, in 2 weeks, sorry, we have a new talk that is for people who are interested in how to store data in tape. So if you are running out of storage space, your lustre, this quota is expiring, and your project ends in December, well, no panic, no panic. There is in 2 weeks this talk by Daniel Heitebrecht at DKRZ and Karl Hermann Wieners from Max Planck Institute of Meteorology, and they will show us the tool they developed. It is called PackEms. So yeah, how to pack you 100 gigabytes of data for tape storage. So now I give the room, please, to Christopher, who is gonna introduce his topic. Dr. Christopher Cado is a climate scientist with focus in Earth system modeling, climate change and prediction, and of course machine learning. And he did his PhD in the Freie Universität Berlin in Germany. So please, Christopher.
Thanks, Maria. Thanks for the introduction. So welcome everybody to the DKRZ Tech Talk. I think it's number 4 around machine learning at DKRZ. So I will start first with talking about the DKRZ Machine Learning Research Group. And then Tobias will take over and talk about the Helmholtz Artificial Intelligence Support Group here at DKRZ. And then his colleagues, Frauke, Caroline, Felix, and Jakob will also say something about their projects there at the moment. So, let's start then. So the DKRZ established last year a permanent machine learning research group, and we call it Climate Informatics and Technologies. So if you wonder, like, what the heck that's to do with machine learning, so climate informatics is basically a combination of words which hints to artificial intelligence, machine learning, data mining, deep learning in climate science. And the other part is the technology part. So we are also big in software development, data analytics, evaluation and validation. So some of you know me from the Freever project. And we also look into HPC structure. Of course, we are at the German Climate Computing Center. Here, greetings go out to Eto and Martin, who are in the group as well and are more on the right side here. So, but let's get back to machine learning. So what we want to do is exactly that, what I said before. We want to work on the interface between AI, ML, and climate science. We want to do that here at the HPC infrastructure at the DKRZ. We want to work really on the knowledge transfer and method research for the climate community. So basically for you. And we really want to have a cutting edge or high-end technologies ready for climate scientists to make your life a little bit easier and maybe produce more science around ML technologies. Okay, great. So I was asked to give a little ML recap here. And this basically means we are talking about cats and dogs again. So I want to just sum up some methods which are pretty common to everybody. So the first one is supervised learning, which basically is a classification problem. So you have two things which you label, and then the algorithm learns that. And the best example are always cats and dogs, like I show here. And so we label these photographs, and then the algorithm learns that and is able to differentiate between dogs and cats. In our research world, this could mean, if you think about climate prediction, I'm pretty sure most of you are familiar with that. If you put that into a deep learning algorithm, into a neural network, and we train with observations, so we basically label with the real world, and then produce climate prediction as an output which comes through. So this could be like bias correction or signal to noise approach. It depends a little bit on your what you do, but this would be a research example from climate prediction. Okay, the second biggest topic or method is the unsupervised learning. It's basically without labeling. So let the algorithm decide what could be different. So, and here the example now has cats, dogs, and giraffes. Yeah, I know, this is pretty amazing. So the algorithm has no idea what these are, but it kind of figures out on its own what is the difference between these three animals and how are they kind of differentiable for such an algorithm. In our research world, this could be, for example, if we have climate observations in the past and we pipe that through the algorithm and a deep learning, deep neural network. And then we have kind of two climate observations, like a little bit the sketch on top. And then it could be that, for example, differentiate between years with and without volcanoes as a climate example here. The third biggest thing is kind of the reinforcement learning, which works basically with awards. So the donkey and the carrot is a really, really good example for that. If you Google Mario IO, you find a pretty amazing video on YouTube where basically Mario runs through the game and it has no idea what to do, but it tries to get as much points as possible. And therefore, the kind of the neural network gets better and better over time. And then kind of the algorithm kind of learns where to get the reward and then gets better through without telling Mario what to do. Okay, so in research in our climate world, if we think about predictions, it could be that we input again into a deep neural network or climate prediction, and then reward it, for example, with the global mean temperature correlation or the root mean squared error or some other skill or metric or something. And then therefore, we kind of reiterate until we have a new climate prediction for this algorithm. So this is something I'm really looking into. So if someone already does that, please call me or write me an email or wants to do that. I'm really interested in that stuff. I haven't seen a lot actually for reinforcement learning. So yeah, so much for the ML recap. I want to start with a really cool video from Louis et al. In 2018. I saw this 2 years ago at YouTube. It's basically a YouTube video here. And they basically did this image inpainting for irregular holes using partial convolutions. So I had all these methods in mind. I just told you, and then I just started watching this video, which basically is doing on the left side having a photo, an image, and it kind of make the image kind of delete things from the image, a little bit like paint in the past. So, and what on the right side you see is that the AI algorithm or the machine learning algorithm tries to make the picture real again. So as close as possible. So we just deleted a bridge here. Now we delete a stone. And that is quite an interesting video. So what you have here on board is something like an interpolation in the color space. So it really kind of takes that picture, looks for the color scale in the picture, and it kind of does an interpolation in the space. So if you have kind of white, then it also whites out. If you have black, it blacks out. But it also, if you go to the next video, it also knows that if we delete an eye, that it must be an eye. And this is a pretty remarkable thing. So this is basically what we have in our field in pattern recognition. So if we train the algorithm with faces, its nose, ears, it's whatever, so it recognizes that it's a face and puts back in an ear or an eye. And these are two things which are pretty important in our field. So the kind of the interpolation in the color space and the pattern recognition. I really love that last part of the video where they have this old white dude and he gets younger and younger and more beautier and beautier, because this comes back to the question, how do you train your model, and are you making things right for the right reasons? If you train your AI model here with young women and you start to repair an old man, it gets female eyes. So, and this is, I think, a really important thing. I love so much that NVIDIA kept it in this thing. This was pretty amazing, this video. So, so we have this technology out there, which was 2 years ago pretty high end. So the question was, can we use that for climate science? And the basic idea, which right away came in my mind, besides like satellite data, was that we have these observational data sets in the past, which have a lot of missing values. And what you see here is kind of the temperature data sets for Headcrut 4, in gray, the missing values of 2018. That's the annual mean. So if a month has no value, then kind of it gets kicks out for the annual mean. And this is already a really, really good picture, right? So if you go to 1850, where Headcrut 4 starts, for January 1850, you see how many missing values we have. So basically, can we kind of bring this thing here to life in our climate science world? That was kind of the question. But how? Okay, the idea here is transfer learning. And as you're all climate scientists, basically, I'm pretty sure you will kind of get into this whole scientific scheme I will talk about now. So what we need in machine learning is always training data sets. If we have a classification task like we have here, we need a lot of data sets. So what we did is we took the 20CR reanalysis data set between 1870 and 2009, which is basically one atmospheric model with some boundary conditions, and it has 56 ensemble members. So we took 55, put one member aside, and then we got over 90,000 training sets, months in our world, images in the machine learning world. And then we took from Headcrut 4 the missing value mask between 1850 and 2018, so over 2,000 masks. And we're able to train our AI. We did some verification sets. You basically take 10% out. And then we have a little neural network, which is trained by 20CR. And then we could like take the 56 ensemble member and mask it with the missing values from Headcrut 4 and pipe that through the neural network. And then we got the reconstructed one. So if you got this already, everything is good. So the first thing I heard when I talked to a scientist was, yeah, but the 56 ensemble number is really close to the rest. I mean, come on. It's probably not so hard to reconstruct. And of course, so a good way to test that is to take a complete different other training data set. I took here the CIMA5 historical data sets between 1850 and 2005, which has nothing to do with our observed world, besides the trend, of course. We have 35 models and 145 ensemble members. Again, took one member out, took 144, around 270,000 pictures, images, or months in our case, and did basically the same thing with the missing value mask, built the setup, trained the neural network, then took the last member, which wasn't part of the training, masked it with the missing values, and pipe it through the neural network and reconstruct it. And then we are able to cross-validate, because we have now two neural networks, and we could also pipe the CMIP one through the neural network from the 20CR and reconstruct that, and the same goes for the 20CR one. And then to just, I know the street is very, very long here. What we want to do, of course, is like reconstruct Headcrut 4 in the end. But we need that cross-validation to make sure everything is correct. And that's basically the setup. If you have questions to that, because that's a very, very important thing, so we can discuss this later on, how this works and so on. So let's move on. So just to give you some ML techniques which are part of it. So it's a deep neural network behind, it's a CUDA accelerated one. It uses partial convolution, so a convolutional neural network, a so-called CNN, which basically folds everything down for the cats and dog thing. Here you see a tiger and a lion, and says basically, yes, it's a tiger, or no. And then we use the UNet in architecture with that partial convolution. So basically fold everything down. So we are folding it down like in the normal thing, and then we're folding it up again. And that's you have a unit structure. I will not go into the details here. You see, we pipe everything here into this neural net. Okay, I did some pre-research. I know some of you might be interested in that, how that works. I'm a climate scientist, so kind of was also a tough thing to jump into. So finding a computer with GPUs took me roughly 1 day. Installed the original software, downloaded the ImageNet pictures, 3 days. They have a lot of images out there with cars and trees and that stuff. Then run the software in its original mode, took me 2 days. And then I had this. So basically, this whole setup from the original paper with photos out there, with missing values and so on. You see here kind of the setup. Then the next step was producing JPEGs, because this whole thing, of course, works with JPEGs, from the climate data, and then run it. That took me 3 days. Producing JPEGs from native data is also kind of a pain, actually. But this was quite interesting to see that it worked, basically. So if you look at, I probably can't see my mouse, right? So if you look at the upper row of these JPEGs here, they have some remarkable reconstructions in the middle where we have basically no information. So I was quite satisfied that we can do this. So, but then the big thing started, change the AI software to read climate data, basically NetCDF or HDF5, run and tune, change the neural network, so on and so on and so on. This is kind of a really big thing. I will not go into the details here with the technical part. It took me roughly 2 weeks. Okay, but then this whole thing was done. It was trained. Took me in the end 1 day. So if we have, for example, a picture here from the 20CR, it's kind of the original one, and we mask it with the missing value mask from head code 4, and put it as an input, and then we get the output of the AI. And we were quite happy actually with that result, what we see here. So basically the warm Pacific, which we took on purpose here, is kind of good reconstructed. If you look over over Asia, this blue pattern, which is kind of is a really good one. Not everything is perfect. If you look over Alaska, but we were quite happy with these results. So what we could do, the next thing, this was kind of the 20CR on a 20CR data set. We were able also to take the CMIP AI here. So the neural network trained by CMIP data. And this is what you see here. And that was kind of the big surprise. So basically the reconstruction from the CMIP AI and the 20CR are basically the same. That is a really good result, because in cross-validation, that means it worked. If you look at the cool Pacific example, it also worked. And if you put it on the other side, so see if 20CR AI is able to reconstruct the CMIP one, it was also possible. Look just over the cooling pattern, for example, in the third row. But of course, we are in climate science. We do a little bit more than just looking at pictures. If we now take, for example, the 20CR time series, which was not part of the training, and make an annual global mean, that's what you see here. And if we mask it with the missing values, you see this line. So basically, no difference in the end, or a little bit difference, but not, but a lot of difference in the beginning. So if we now reconstruct our field on picture to picture base, so month to month, and then do the annual global mean, this is the reconstruction here. And this worked pretty good. So we were pretty close to, much closer than the masked one. And the interesting thing now was with the CMIP AI, it's basically the same result. And this was quite, this brought in some confidence that we can do in the end, also do this with head code 4. Just to give you some metrics here, with the mask one, you got 97% of correlation, or 0.97 correlation, and root mean square of 0.11. And we have a higher correlation with the 2 neural networks and a lower error. We did other stuff with kriging and PCA. I will skip that here for that talk. Then we went to the reconstruction. So we were quite confident that this works. So, and what we took in the reconstruction, in the spatial reconstruction, was a particular El Nino case. There was a rough El Nino between 1876 and 1878. And we had roughly El Nino for the whole year, so even in July. And that case in July is particularly interesting because we had heavy rainfalls over South America. And when we look at head code 4, we have a big hole of information in the Central Pacific. So the interesting question was, can we get some signal out of these reconstruction from the neural networks? And this is the reconstruction from the 20CR AI. And we were quite happy with that result. I know there's no way to kind of evaluate that against real data, because basically the real data is on the top. And if we compare it to the CMIP AI, it also is not as strong, but it also suggests a warming pattern over the Central Pacific. Just to give you an idea, if we use kriging, basically just interpolation, that is the picture here. I know it's not a fair comparison here. I will skip that due to a matter of time. Okay, so then in the end, of course, what we want to do is climate science here. That is headcrud 4, the annual global mean reconstruction. You probably know from the IPCC report. That is the general picture we have usually in the observation chapter, including missing values, of course. So if we now put in the headcrud 4 reconstructed one by the 20CR AI, our reconstruction looks pretty good on the later stage. It is not the same, but it kind of suggests that we have, especially in the beginning, we have a much more cooling. Let's put in the CMIP AI here, which again suggests roughly the same result. And if we analyze that here, so we see the trend patterns are a little bit higher because of the cooler early phase. We have the cooler global mean temperature from the mid-19th century to the early 20th century, an underestimation of the global mean temperature trend between 1850 and 2018. The results support other studies, which already said like headcrud is a little bit too cool in the mid part here in the picture. And we have also, like, we agree on the weaker hiatus phase, like the famous kriging paper came out in recent years. And we have for the highest value, so the warmest year on record, 2016, we have an even warmer year, 2016. Okay. You find that whole thing in a paper. We can post the link to the paper into the chat. This cooperation with NVIDIA and the Free University in Berlin worked quite well. We have that technology now ready, and we want to go further on with this. So after I gave some talks, colleagues came to me and said, I have this and this idea, and some were really, really good and interesting. Just to mention two, Frauke Feser and Oliver Krüger from the Helmholtz-Zentrum in Geesthacht around the storm seams came to me, and they saw this technique, and they have the idea of kind of changing old observational data in reanalysis to kind of get better storm, basically check densities and kind of to check if we are able to produce a better ground field for the storms in the North Atlantic. So for this, we would need to change the variable, and we have to go to other frequencies. And actually, we are just starting with that, and I'm really looking forward if this technology can do that. And then just to mention another cooperation with Mark Rattenhaus from the Visual Data Analysis Group from the Regional Computing Center here in Hamburg. He said, yeah, Chris, that's a fine technology you have there, but I'm more interested actually in downscaling and kind of bringing climate information down to a higher resolved values. And I said, yeah, that's great, because that technology I just used is also possible to change, that we can do downscaling with it, or upscaling in terms of pictures. So we could like mix this, my technology, with the ideas of the original paper, and then we have some downscaling application here. So if you're interested also in that, just let me know. Okay, just to sum up my part. So we have a new AI ML research group here at the DKRZ for HPC infrastructure, knowledge transfer, method research. So we want to bring kind of some really high-end technologies in basically for you, that you are able to use these technologies, and we help you with the transfer. What I showed you was like the last study we did on past observation reconstruction, which is basically a combination of climate modeling, observation, and AI. And we showed some successful refill of climate information input, interpolation plus pattern recognition. And we think this is a really strong tool for climate research. And I showed you a little bit of support and cooperation already, and we want to have cooperation with the DKRZ user base, which is basically you. So if you want to discuss your research and a potential AI ML add-on, so you have an idea what to do, and maybe you want to go on with this, so please let us know. If you have an research idea and want to know how to bring this to life, we could be also helpful with that. If you're already working on ML and want to discuss the research results, which is an important thing to make sure that the AI and the climate science is correct and might make sense, that's also a potential support here. And of course, if you have problems installing the software, then you also can like contact us. And I just want to give you the 4 dots here. Main target is always like our homepage, where you find kind of how to use GPUs and that stuff. If you have problem installing something, the Beratung, our great Beratung, does an amazing job kind of helping you. And if they think it is better if Tobias or I look over these questions, then they forward this to us. So Beratung is always a good channel for everything at the DKRZ. If you directly wanted to talk about research and that stuff, so please let me know. I'm the right contact person. And if you are at the Helmholtz Center, you're kind of a premium customer. So so we are pretty proud of that project. I think they're doing a great job. We have also the cooperations going on with David Greenberg. I think Tobias will talk a little bit about that. So if you're a premium user at the Helmholtz Center, you have kind of a whole group behind you here at DKRZ, which help you with basically everything around AI. And with this, I will hand over now to Tobias. So we will go on with questions in the end we discussed. So you can always pipe something into the chat. I will now stop sharing my screen. Vloop. And Tobias, please take over.
Okay. Can everyone hear me?
Yes.
I guess so. Okay. So thanks for the first part, Christopher. And I will just directly continue. So I'm Tobias Weigel. I'm presenting here on behalf of the whole team. If you look into the chat box, into the participant list, you will also see them. They will also talk to you later. That is Caroline, Frauke, Felix, and Jacob. But for an introduction, I will just say a few things here before we go into some nice case studies. So the whole project here, as Christopher already indicated, it's part of a larger initiative at the Helmholtz Association, which is called Helmholtz AI. Helmholtz AI is tiered into different thematic areas. And basically here in this sort of sub-project, we are responsible for the topic area of Earth and environment. So with the caveat here, of course, it's more than climate, Earth and environment. So also the case studies we have are also going a bit beyond climate or system sciences. But nonetheless, they will give you some insight into what we are doing and what practical things you could possibly come to us and ask for support. To start, the overall part of Helmholtz AI that is here in Earth and Environment is once again divided into 2 groups. There is a young investigator group, really a key research group at HTG in Geesthacht, headed by David Greenberg, focuses on model-driven machine learning. And then the second part of the Helmholtz AI Earth Environment pillar is the consult team here, led by myself, hosted at DKRZ. Roughly, we provide the technical support, counseling, training for users at Helmholtz centers working on AI, ML problems in Earth and environment. As Christopher already indicated, yes, this is sort of restricted to Helmholtz, but I guess if you contact the Beratung and you are not part of a Helmholtz center, we will figure something out. In terms of what we offer here at the consultant team, I have this rough overview slide here. The first box on the top left is sort of what we offer in long term as a knowledge base. So we will accumulate knowledge about methods we use in ML AI problems, particular case studies. As I indicated, we already have some good examples. We will show workflows, how you practically deal with ML problems with libraries, PyTorch, TensorFlow, whatever, on our machines, on storage devices, and so on. The second part, the top right corner box, technical implementation support. This is sort of where most of our work currently focuses on. Means coding for data loading, transformations, everything you need to do before you put some data into an ML model, but also scaling up the applications that we have. So generalizing an application so it can be used across multiple GPUs or even multiple GPU nodes. Data and ML workflow implementation optimization. So really going into the architecture of a neural network design, for example, doing hyperparameter tuning, optimizing based on the results, redoing iterative experimentation, and then of course also doing testing, deployment, generalization of ML code. We also do a small PyTorch subcomponent library work we develop. So this is also part of that. Then in terms of training and knowledge exchange, we had a kickoff workshop earlier this year before COVID-19 sort of grabbed us all. But we plan on having further workshops, of course. And of course, this seminar here is also a very good example of what we do in terms of training and outreach. We also plan for particular training courses. More on that will come. We also hoped at some point to do on-site visits, so really doing some sort of expert exchange. Of course, this is now also stalled, but I guess that doesn't mean that it won't happen ever. And the second, the fourth box here at the bottom right, general counseling, a bit more high level. Basically means we help you understand the methods that ML offers you, choosing the right method for your given problem, but also dealing with limitations and biases, because of course not every method can deal with every problem, and there are certainly limits as to what ML can do and how to work on data, how to optimize, how to do data cleaning, for example, these kinds of things that are also part of the counseling we provide. And we also have running vouchers for that. Now, I've already mentioned this word just now, vouchers. What is a voucher? A voucher is a sort of a support request. It's the basic item that we work on. So we really work as a service on demand. What does it mean? Basically, if you come to us and say, look, I want to have some support here. I have an ML application already, but I want to scale it up. Or I have a particular problem in mind. Can you help me design some ML workflow with this? Basically, you would come in contact with us. We would make a video call, for example, first, and define a sort of small mini project, really a large-scale support document that is written out of that is then handed over to Helmholtz AI, approved, and basically then we can start our work. So don't get afraid here. This is a bit of just project bureaucracy. Basically means we have sort of mini projects running up to 6 months, and in this time frame we also usually deliver some first results and really work iteratively and very dynamically on the problems that we are given. Just as a sort of introduction to the activities that we do, the current cases that we have the vouchers working on. This is just an overview. You can already see there are different disciplines possibly reflected here. So from marine sciences, atmospheric chemistry, but also remote sensing. It's sort of a good range across the Earth and environment spectrum. And also in terms of methods, you can already see here from uncertainty quantification to some feature importance ranking to really benchmarking, so hardware close to hardware. We have a range of activities. And with that, I would now sort of hand over to my colleagues. So Caroline will be the first. We have 3 small cases here, just with a couple of slides to show you, to give you an insight into what really is it that we're working on here on behalf of the users. So let me just hand over to Caroline, who will say something about a project in remote sensing we're working on behalf of GFZ.
Yeah, thanks, Tobias. So I'm going to present this first showcase. And let me just mention a bit about the scientific background of this. So the idea is that the satellite on the right, the Cygnus satellite, uses reflected GPS signals to infer the roughness of the ocean surface. So the scattered signal that is recorded produces two-dimensional power maps that you see on the left. And these look a lot like images. So a lot of machine learning techniques revolve around classifying images and working on them. So this is a very good task for exploiting ML techniques. Of course, there exist classical methods or geophysical models in order to retrieve the wind speeds from these maps. So the correlation power is inversely proportional to the ocean roughness, and from that you can infer the surface wind speed. But the problem is that this contains a lot of biases. So calibration biases, assumptions that go into the model. And what we wanted to explore is a machine learning for a bias-free estimate of the surface wind speed. So really data-driven. And Tobias, can you switch to the next slide? Often people are a bit skeptic about the potential of machine learning. Does it really work? Fortunately, our collaborators at GFZ already did some preliminary work with a fully connected neural network, so really the simplest type of neural network. And they prepare true wind speeds versus predicted wind speeds using both a conventional approach on the left and a machine learning approach on the right. And as you can see, the RMSE, so the root mean square error that measures the error loss function that accumulates across all these samples, it decreases with a machine learning approach. So this is really a sound technique that can be useful. Next slide, please. And we are going a bit farther here. So as I already mentioned, these 2D maps that we record, they have image-like qualities. So we introduce convolutional layers to the neural network that are typically used in image processing. And we combine these convolutional layers together with fully connected parts that process additional parameters of, for example, the satellite or the geometry of the problem. And with this, we are able to refine the prediction even more. So the root mean square error is decreased even further. And this looks really promising as a tool for predicting wind speeds in the ocean. I should also mention, since it's a tech talk, a bit of a technical detail. So we use PyTorch for training these models. They are surprisingly small for this problem, so it's not too hard to describe. And we are able to train on a single GPU in about 5 hours for one model. And the nice thing is that we have about 7 million training samples that easily fit into memory on one GPU. So data loading is quite easy. Next slide.
Yeah, hello, I'm Felix. So I'm presenting another project where we work on replacing parts of a modeling software for atmospheric chemistry, which is called EMAC. And we are working on replacing a part of EMAC that models chemicals in the stratosphere. And so we work with data of about 1 degree resolution and in 63 levels in the stratosphere. And we work with 110 chemicals in multiple time steps, and everything we do is still under development, so under heavy development. So everything we show you here today may change. So next slide, please. So on the left, you can see a rough sketch of our architecture that we use right now, which is a simple, fully connected network. So after a lot of experimentation, we found that training one model per chemical works best. The models, again, in this case, are relatively small, about 1 million parameters. It's roughly 3 to 4 hours per model, so it's pretty similar to what Caroline just described for the other project, for the remote sensing project. And we only train with 6 compounds at the moment, but this will be expanded soon when we get a lot more data. And yeah, this is really a project under heavy development. It's just a glimpse of what we do at the moment. And next slide, please. And here's a preliminary sample result of what we are doing. So this on the left, you can see on the top left, you can see the model output. So what the model would output, how ozone would change in one specific level in the stratosphere. And so if it's red, the ozone level would increase in the next minute, and if it's blue, it would decrease. And on the left bottom, you can see the predictions that our model makes, which at first glance looks almost identical. And but of course there are differences. So on the right, you can see just the difference between the two pictures essentially. So the model is not perfect, of course, but also on this preliminary development stage, for this particular chemical in this level, so it doesn't work as well in all levels for all chemicals like that. But in this particular sample case, the error is like on an order of magnitude lower than the values, but still it's only a prediction for 1 minute in the future. It's not really clear how that would work for using this model for predictions of months, for example. If errors would accumulate, that is not really clear. But as I said, this is a glimpse of what we are working on and what we are doing. Thank you.
Yeah, so with all these use cases in mind, you can probably imagine that there's many technical challenges as well. And we're also looking at these and kind of trying to figure out how to scale machine learning to HPC resources. And for this, we are working with colleagues from HCG to better understand these bottlenecks and also the performance implications that these workloads impose on systems like Mistral. And one interesting use case, for example, is this weatherbench case study. So in the top, you kind of see that you need input and target pairs, and from those you can create a prediction using these neural networks. And this is kind of challenging for the systems that we have today, because basically we are taking raw netCDF data, and then we have to do random I/O across terabytes of data. And so in many cases, you will find yourself in a situation that you have all these files and you coordinately seek individual pieces of data from this. So you need to load a lot more data than you actually want to produce these input target pairs. And maybe you switch to the next slide, please. And so basically, we're looking at the whole pipeline to optimize these use cases and take advantage of the resources that we have. So as already mentioned, we have something like these workflows where we have raw netCDF data, but we have application or domain-specific transforms that are needed to reshape the training data. So that might include normalization or cropping and upsetting and subsetting. But there's also storage optimization transforms. So we might want to alter the serialization on disk or the striping to take advantage of the parallel file system. And on the other hand, we also have many challenges where we have to care about distributed memory management and then scaling to allow parallel training. So on the very right, you kind of have different pipelines where you start in the simple case and you might allocate just a single node, and then things remain kind of simple because the frameworks are really forthcoming. But then as you scale it up to multiple nodes, you have to take more and more advantage. And a lot of the established machine learning communities don't really necessarily cater towards the use cases that you would find yourself needing as a climate user. And with that in mind, we thought it might be a good idea to close with our most common inquiry. Maybe switch slides. Yeah, thanks. And that is kind of how can I train things on Mistral using GPUs? And to save the trouble and the frustration of maybe spending multiple days of getting an environment set up, we kind of thought we'd end with one possible way to get started with PyTorch. So you might, if you have a Mistral account, switch to your work directory, download a recent version of Miniconda, and then install that, and then activate that. And to sidestep some of the compatibility issues that you might find on Mistral due to CentOS 6, it's a good idea to downgrade to Python 3.6. And then if you want to take advantage of the GPUs, then you can just install PyTorch minus GPU, and that should give you a working environment with PyTorch that also allows you to run many notebooks that would take advantage of the GPUs. Now, this is typically a slightly dated version of PyTorch. So if you need to leave on the bleeding edge, things get a little bit more involved. But basically, we have options for this, and we're happy to help. So we have versions and options in spec, but also in Singularity containers if you care about reproducibility. So feel free to reach out, and I would say I leave it with that.
So thank you also to Caroline, Felix, and Jacob. And just here, I'm sort of just closing up here, just my sort of last content slide, take-home messages, very quick summary. So AI ML support, we have that available via Helmholtz AI at DKRZ. So if you are now thinking about specific case problem, just come and talk to us. We make a video call and we can discuss. As you've seen just from the glimpses here, the three examples, we have a diverse set of use cases from the wider community, not just climate. It's really Earth and environment in its full range. The experiences with practical environments, what just Jacob showed, for example, we are gathering more and more of that. And of course, maybe this last point is a bit more strategic. We see increasing use of the DKRZ GPU nodes for ML. This is good, of course, but also it is something that needs to be pointed out a bit more. Some awareness needs to be raised, because if there is increasing demand, then certainly we have to think about the needs for additional GPUs, for example, in the future. But basically, we need to have cases for that. So think about this, talk to us, and yeah, please don't hesitate to contact us. Just here at the last slide, how to get in touch with us. Just as Christopher showed, really the first call can just be the Beratung. But also, of course, you can contact any one of us, Christopher, myself, the colleagues, just writing us an email. The names, once again, are here at the bottom of the page. And please don't forget about nice things that also happen. So one is the machine learning seminar led by David Greenberg at HDG every 2 weeks on Tuesday, 3 o'clock. It's streamed via Zoom, but also via YouTube. It's fully open. More information is on his website. And as Christopher already showed, the machine learning mailing list is also there, which we use for announcements. With that, yeah, I'm closing up here. Thank you for your attention, and we are now happy to take questions.